Okay, salam everyone. So we are going to have an asynchronous mode for the lecture today. So what I'm going to share to you today is related a bit more on theory, and after this we also have to do some programming. So we need to know few softwares, and we need to write down some things and do the simulations. So for the first few programs, I'm going to have a very basic programs on how to work on, and then we are going to have further later in our lectures for the rest of the weeks. Okay, so today we go back to the lecture about the theory. A few more theories that we have to know. Basically, it's related more on the what is inside the microcontroller itself. So I'm going to look at this one. All right. So this is what the microcontroller looks physically versus the block diagram over here. You can see that inside here is a combinations of all of these CPU and the modules here. So this is what you call modules. There's a modules one by one. This is related to the semiconductors area, where this is a wire bond everything. This is they will call it I forgot this one, the wafer. This is where the transistors are located. And so we go back to recap the memory, types of memory, and also the difference on it. So we have the ROM, we have the EEPROM, and we have the RAM. So again, this is actually the place where you are going to put the hex file, which is your program, and this is by burning or flash it. And then you have the RAM. This is where you can change the location, the locations, and this is where you're going to you're doing the setup on your microcontroller. Basically, most of it happens here because it consists of two types of registers, which is the general purpose and special function registers. And then finally you have the EEPROM here. This is similar to ROM, but the difference is it can be changed during operational when your program is executed, and then you can change and save something to the EEPROM over here. Okay, so this is the RAM. The RAM is mostly that you're going to change it to set up your system. Okay, this is what I'm going to teach you later and afterwards. Okay, this is basically about the program memory organization. So this is basically the parameters or the specifications on your program memory. So we have the 13-bit program counter, and this is capable of addressing 8,000 words times 40 bits program memory space. So by using this 13-bit, it can address up to this particular totals of memory space. So this is a reset vector at this location. This is an address, and this is an interrupt vector which is at this address. This is inside the microcontroller ROM. The ROM also you have to know that there will be an address for it. So I'm going not to touch very deep on here. So we are going to move forward. So this is what is inside our RAM. Okay, RAM is the one that random access memory, right? So you can see that here there are a lots of special registers with its address. Okay, these registers, they got names over here. So you can see that this is registers. You can see that each of the registers got names. So most of the time we are going to play with the register to do setting up, or to give signals up from the microcontroller. Okay, the signals, okay, this is later I'm going to show you later in the Proteus diagram. So today we are going to play around two types of registers. One, they call it port registers. This is, you can see that port A, B, and C port. So by general, it has the port and the port names over here. And then we also have a trice register name, which is also ABC. This is the one that we're going to play today. So there will be the difference on that, right? Okay, So anyway, this is only the structure of it, so it's not really important at the moment. I just want to teach you how to use these types of registers. Okay, again, next one is this is status register inside the RAM. Also, this is how to read a status register. The register size is a 7-bit. Okay, this is bit 0 to bit 7. You can see that if you go back to this one also, all of that got 8-bit of size, basically from bit 0 to bit 7. So the size is around 8-bit. Okay, now look at this example here. So this is status register, and then you have this is example of PIC16F8 memory map. So this is not really important. This is not like the PIC16F, but roughly this is like the how the memory map works over here. Okay, and then for the RAM, you have two types of them, which is the general purpose. Okay, and you have the special function registers. This is where it has the core and peripherals over here, this type of RAMs, where the core is basically main on the register, which is to control and monitor the applications and the process in the central processor. Whereas the peripherals, special function registers, mainly control the operations of peripherals unit. This is more on the module itself, which is example on the serial communication module, the analog to digital converter, and etc. Okay. So next one. So this is the how the core registers. This is the parameters of it. So you are not going to learn most of it over here. This is roughly how do you set. Okay. For example, this is how to set, and this is the value when you need to set it. For example, if you want to set it 1, so you're going to have this one. This is how to set. Okay, we're going to look at the example to make it clear. Right, then you have the option register. This is another core CPU which is going to be learned in chapter 3 or chapter 4. This is quite important registers that you're going to play around. Okay, prior to that, how to works with the with the microcontroller, right? So if you look at the analogy of the car, so you can see that the functions of a car versus microcontroller, what are the basic components and the tools needed. So here is a car. What are the things that needed for a car to be moved or to function? So this is analogy that we have over here. And how about PIC? So what are the basic things need for it? So you can see that on the next page is this is the PIC. What you required, the basic thing is the clock here, and then you have the master clear circuit to reset it if anything happened to your microcontroller. And the most important circuit is the power circuit. Okay, your PIC requires only 5 volts, not more than that. Okay, so here you're going to plug in, and this is a regulator which is going to have, maybe this is a 240, right? 240 volt from your power, and then this regulator will only give 5 volt out to the microcontroller. This is a power pins, something here, something here. So it means that without this power, it cannot work. Without this clock, it also cannot work. This is very important to have because this one can reset the condition of your microcontroller. So if you push this button, then it will reset. Okay, so there are 3 things. One is the power supply, second is the clock, and the third one is the master clear circuit. So you have to remember all these things. Okay, next one. So how to power up a PIC by a basic wiring. So you can see that again by referring to this one, right? We have the power supply. Here you can see that this is the power supply here again. This is a regulator, and your output will be 5 volt only. This is around this volt. Okay, then you can see that the master clear circuit, you can see that this circuit is a low active, where when you push down the switch, this is going to be low, 0 volt, and it will reset the whole system. Then you have the clock here, and again this is a capacitor. This capacitor is to filter give you a good signals of a clock. And then you have this power supply, which is coming from this guy. Okay, 3 components there. The master clear here, the clock, the power supply. That is the thing that you need to have a basic microcontroller system. Without this one, it cannot work. Right. So in this image, this is not used anymore. This is very old board. This is basically your microcontroller, and this is your board. This is your regulator. This is power supply and regulator here. This is regulator, which is you have maybe 240 or maybe 10 volt DC, right? Going in and then power in your system. Okay, so this is your reset button, which is connected to pin number 1 here. And you have the clock. This is clock. So this is clock. This is reset button, and this is power supply. This is how it works. This is how it looks basically. But this board is not used anymore. So we are going to use other things. I mean, there will be the full sets that you're going to use it, which is on the board itself. Okay. So the rest is about the software, which is the compiler. We are going to use MicroC here. So we have so many compiler here basically. So we are going to use only one MicroC here. And then the function is for you to write. The function for MicroC is to write your code and to translate it, which is to compile it for hex code. This hex code will be used as a machine code and will be simulated, okay, in your Proteus. So next one will be your compiler. This is your MicroC again. So you can see that this is how it works. I'm going to show you guys how to do it. And then you have the simulator over here. Okay, this is a simulator, and then you can simulate the programs that you want to have. Okay, so there are the 2 softwares that we are going to use today. Okay, let's do a very basics program. So you can run your MicroC. Okay, so this is your first page for your MicroC. Okay, so you can start by using a new project here, new project, then you click next, then you select your device, which is PIC16F877A, proceed. Device clock is 20 megahertz. Okay, next will be this one, project file name. Specify where you want to project will be saved. So I'm going to save somewhere here, coding examples, maybe at another new folder, class test. All right, so here you can put class test, which is a CCP file here. This is your project file here, class test here, and save it. And then next, this one no need to add anymore because you don't have any library or whatever files that needed required. You remove everything. So just put next, and then include all by default, and then next. Finish. You complete your workspace to do the first program. Okay, here this is by default. This is your body of the program. So C++ will have this one void main. You have to write down all your code inside this body. It must have void bracket and what is this? Called hyphen. This is another bracket. This is actually bracket. This is curly brackets. It must have open. It must have close. You cannot have only one. This one deleted, which is a wrong syntax. Okay, let's look at the theory behind. So I'm going to draw something here. Again, for your sorry, I'm going to open up here the PIC here. Hold on. Okay, open up this. Okay, let's go back to the pins for PIC last time. Here. Okay, remember this? So we are going to play part B today. So by looking at this one, right, part B is over here. Remember that when I say that RB, this is notation for the digital input output only. Whereas for port A, we have RA1 and AN. AN, it can be digital or it can be analog input. So this is going to be a digital input output. Okay, so starting of the program, you have to set which port that you are going to work with. For example, here I'm going to work with a port B here, one of the pin to turn on an LED. Okay, so how can I write the program? So the first thing is you require to set the port B either as input or output. But because of LED is basically an output, so you have to set port B as your output. So how to set? By using the registers here just now, right? The one that you need to set up whether it is input or output, you have to change this value, thrice B for port B. This is 8-bit size. Okay. So if you set this 8-bit here, okay, this is bit 0, right? This is bit 0. You can only set either 0 or 1 only in this registers. If you set it as 0, this bit is going to set pin RB0 as output. If you put all 0, means that you are setting up port B pin 0 to pin 7 all as output. If you change this 0 to 1, for example here you put all 1, which means that you are going to change this port from port 0 to P7 all as input digital input. So you know that this is going to be each of the bit is referring to the pins for port. In this example, we are going to have port B, right? So this is going to be referred to port B0, B0, and then this is going to be B7. So how to do that? In your MicroC, you can start to do the setting up of your input-output by typing trace, which is trace B, which is at port B here. This is trace B just now, right? So you're going to change this value here. This is the one that you're going to change here. So I'm going to change it as output. So trace B is equivalent 0B, which is saying that you're going to put as a binary value only, which is 0 or 1. So I'm going to set it up all 0. 1, 2, 3, 4, 5, 6, 7, 8. And then you have the semicolon. Okay. This command is saying that you are setting up all the port B as output from pin 0 to pin 7. Okay, if I change it like this, right? If I change this one 0, 0, 0, 0 to 1, 1, 1, 1, means that I set up pin 0 to pin 3 as input and pin 4 to pin 7 as output. So you can see that here, for example, just now, RB0 to RB3 is equivalent to input, and RB4 to RB7 is equivalent to output. Accordingly to the setup here that I have, you can set up any configuration that you want, as long as it's 0, 1 only. Like, for example, you have 0, 1, 0, 1, 0, 1. Then you know that the even pin numbers is going to be the input, because 1 is equivalent to input. Very simple. You can see that 1 is equivalent to input, and if you set 0 is going to be output. Same like goes to this one. So this is 0 is output, 1 is input. So by having this statement, right, you are setting up port B on each pin, the function of it. Trace B is for digital input output. So to make life easier, first we are going to set up all trace B as output. Okay, so this is the first line. So after that, you have to do a looping, which is they call it while 1 bracket 1 bracket curly bracket close curly bracket, and then you have to write the command here. This is the looping command. This is to set up. This is a looping command forever. This is a loop. As long as you don't reset it, it will loop over here forever. So right now, I'm going to turn on my LED, because after I set up port B as output, I want to turn on my LED over here. So you can see that the register that you're going to play around is this register. The name of register, they call it port B. This is the name of the register, which is coincidentally, I call this port is port B. This is the name, and this is the name of the register, which is two different things. Okay, this is quite confusing. This is port B, this which is the name I call, this is the port B. But when you want to send signals from this port, you have to change the value in this register. Again, if you change it to 1, you are sending 5 volt out. If you change it to 0, you are giving 0 volt out from the pins. Okay, this port B. So you can see that in this program, so you can turn on an LED by giving 5 volts out. So the command will be port B is equivalent to 0B. Again, this is for binary. So you're going to give all 5 volt from the pins. You are going to put 1 1 1 1 1 1 1 1. This is the command. Okay, this is the command. Very simple command. This is how to turn on the LED. So now you have this command. You have complete the first basic setting up input output, which is going to be your output LED over here. You can build your program. This is a must because this is C language and your system must have hex file, which is this one. You can see that finished successfully. You go back to the directory just now. Here, directory. Hold on, let me open a directory for you guys. So module C, teaching set modules, coding example just now. You got the class test. So you can see that from one file, after you compile, it has all these things, and this is the one that you're going to use, class test.hex. Okay, now you can run your Proteus. Okay, you can use ICs here. Then you can start to get all the components. You click this device here and click P. Then you type PIC16F877A. Okay, so this is the first one. The second one you require is LED. So I'm going to take the LED, the bright color one, which is yellow LED. And then you have the resistor, call it RES, resistor. Then it's okay. Okay, first you just look at your LED, the PIC here. This is without any components out. When you do simulations, you no need to put any power supply or ground to any pins. You just double click and it's working fine because this is actually a simulation. So we just want to look what we are going to have just now. We are going to put the hex file here. Just now this is the program file, which is the coding example just now, which is the class test. This is the one. And then the frequency will be at 20 megahertz. Okay, just put over here first. So here you can run your simulation. Click here. So you can see that this is changed to all red because you are giving 5 volt signal. So you can stop this one, right? You can stop this one and then stop the simulation. So let's change again the file here. Instead of giving 5 volt, you are going to give all 0 volt. 1 2 3 4 5 6 7 8. So this command is giving all 0 volt to port B. So you have to compile again. Why this one? This is you have to compile, right? So this is build. So you can see here the class hex file is here at 10 p.m. is updated, right? So this is updated. So go back to your Proteus. Okay, already have this one. Then you run the simulation. You can see that the value out from here is 0 volt because you set this one like this. And then this is the results when you put the output for the trace B. Let's try to change this one to maybe 0 1 0 1 0 1 0 1, right? compile again. Then this one you stop this one. And then I think it's already updated, right? This is already updated. 10.1, yeah, it's updated. So, okay. So you can run this one. Just run it. You can see that the result is like this, is 1 0 1 0 1 0 1 0, which is the same one like this one is 1 0 1 0 1 0 1 0. Okay, you are giving 5 volts and 0 volts by using this command port B. Okay, so let's try to put the LED over here. I have this LED yellow here, and then put here 1 and put here 2. So let's try 2 only. And then you have the ground. You must have put ground here. Ground is at this one, and then you have the ground here, here, here. So I'm going to have 2 pins only. So you have to go back to this one again, go for this res, which is the resistor, and another resistors here. Okay, let's try to put it to this one first, and then you have this one here. Change the value to only 1K because this is very very high value for a resistor. Okay. So you have all this connected, and then you just run it. You can see that your LED here is turned on by having these red value signals, which is 5 volt. This one is not turned on because of this is 0 volts given. Okay, so your program says that this is after you set up as output, and then this is going to be turned on like this. If you, let's say for example, you don't understand this one, right? So let's try to change this one to all input setup, which is 1 1 1 1 1 1 1 1. So by looking at this program, you know that trace B port B is actually going to be as an input, but you are not using this schematic as input because LED is output. So basically there will be no turning on of the LED. So let's try. So this is all input. Just build this one all again. And then you can try again. So stop this one, run this one. So you can see that without having any connections, this is all nothing. This is waiting as input. Now you can see that this is coming from a ground, right? So this is coming from a ground, so the input is 0 accordingly over here. So ground is 0 volt. So this is an input rather than output. So you have to set up correctly, which is all output. Okay, again you have to compile it. Then try again. Run this one. You can see that this is the one that again that we have. This is correct one. Yellow, and no, it's not turned on. This is turned on. This is not turned on. Okay, so you can see this one. So let's try to do a blinking LED. It's very simple. So you have this is correctly set up, and then here what you can see that what you can do is you can put a delay underscore ms in 1000 milliseconds, and then you give another command which is again port B is equivalent to 0B. Then you invert all this thing is going to 10 10 10 10, and then command here, and then delay again underscore ms 1000 semicolon. So here is going to be turn on, if you look at this particular bit only, this is going to be turn on, delay, turn off, delay, and then it will loop again forever. This is a looping, so this is going to be turn on, turn off, turn on, turn off, and it will keep on looping. So let's try. Build again. Okay, go back to your Proteus, stop this one, and then run again. So you can see that it's working correctly. So the command is very simple. This first one, you must set up your port as any input or any output. And then if it's an output, then you can play around like this. Okay, so this is how it works on the tri-state. Input, we are going to have an example of switch. Switch is going to be maybe another YouTube. I'm going to run it again, but maybe next time. But you need to understand first this one. So it same goes to any port which has the name as RB, RA. You can play around with the same thing. RD. This is going to be quite simple. If you want to play around with port D, you're going to tries D, blah blah blah, tries A, blah blah blah, something like that, and tries C, something like that. So you're going to set up again like this one again. It's up to you how you want to set up. Okay, this is how you set up, then you can play around this one. Okay, so this is how to turn on your LED. I think I'm going to try the switch later. I think I want you to understand first the concept, how you want to change the register here. Remember that this register is at your RAM, and then you are going to have it this location change by setting up the value inside here. So each of the RAM size is 1 bit size. Okay, so this is a basic one first. You must try how to turn on, how to use Proteus. Okay, keep on playing first, and I'm going to give you assessments in the ULearn. Okay, that's for today's learning process. I'm going to give you more later. So thank you very much for the time.